Documenting interiors of historical monuments is an exhausting task, especially in areas that are difficult to be accessed without a static infrastructure. We present Dronument, an aerial autonomy for interiors of historical monuments which cooperates fully autonomous drones in documentation tasks in areas high above the ground, without scaffolding installations or mobile platforms. This novel universal technology makes high-quality photos and videos much faster, safer, and repeatable than ever with conventional technology. With the help of onboard laser sensing, autonomous drones can be deployed in arbitrary lighting conditions. In interiors of varying dimensions, ranging from small chapels to large cathedrals, and in environments without access to satellite navigation while being filled with all kinds of obstacles. Additionally, the multi-robot coordination allows for performing tasks that to this day could not be performed outside the laboratory at all. Before any flight, the environment is scanned with a ground laser scanner. This scanner produces a point cloud representation of the structure used by the robots during their flights. The point cloud is converted to a three-dimensional mesh model for specifying and planning the autonomous missions. During specification, a human selects a set of viewpoints to be captured. In planning, the drone trajectories are planned to capture all the viewpoints under the desired illumination as fast and safely as possible. Only after the robotic plans are verified in simulations, the autonomy is deployed in the real world. The autonomy is decentralized and runs on board the drones in real time, with only an external base station supervising the safety of the flight and reacting to possible failures. The drone's autonomy perceives and maps the environment, and follows a trajectory planned and validated before the flight with centimeter-level accuracy. To do so, the drone utilizes up and downward point distance lasers, a three-dimensional laser scanner producing up to 5 million distance measurements per second in a 90-degree vertical field of view, and a front-facing RGB depth camera. The payload for the documentation task is modular and swappable. In this case, a high-resolution mirrorless camera takes pictures in the visible spectrum. This camera is actively stabilized, and its lens is easily interchangeable. To improve the quality of the photos, the drone also carries a light illuminating the scene directly. The desired viewpoints selected during mission specification are captured accurately in high quality, quickly, and safely during the autonomous flight, in which the drones reason about their sensory data, estimate their state in the environment, and use the information to control and optimize their motion while following the pre-planned three-dimensional trajectory. Aerial photography is also supported in the commercial sector. However, the available products provide an insufficient level of interior autonomy, do not offer multi-robot solutions at all, and are unable to capture high-quality details in poor lighting conditions. Direct lighting from the camera drone can compensate for insufficient lighting in dark areas, however, it causes the captured object to look flat in the resulting image. Distributing the light to a secondary light-carrying drone allows for illuminating the scene from other non-direct angles. This helps to reveal the three-dimensional structure of the scene and is useful in highlighting the roughness and crevices on the surface. The cooperative navigation of the drones is achieved using decentralized algorithms respecting leader-follower architecture, running only on onboard computers in real time. However, deploying multiple drones in a shared environment requires an identical understanding of their surroundings. This is achieved by having a shared frame of coordination which is automatically deduced right before the takeoff. This calibration process uses the robot's sensory data to find their global poses and hence match their coordination frames together. Among distributed lighting techniques is RTI, the reflectance transformation imaging. RTI is a rendering method enabling to view an image under an arbitrary direction of illumination. To do so, it requires a set of pixel-aligned images of the object under illumination from various known directions. We have transferred this method from laboratory to large-scale real-world areas not easily accessible by people. To compare the results of our method, we show the resulting PTM representation as obtained from images taken from the camera drone on the left and images from a stationary camera on the right. In both cases, the scene is illuminated by an autonomous drone. The operational space of drones makes them also practicable in three-dimensional mapping. On the left, you see an inaccurate model of the altar reconstructed from ground data. On the right, the same altar is built from data of the drone. It is clear that aerial mapping can assist in fixing inaccuracies or can be used single-handedly. Aerial photography can be utilized outside the visible spectrum, where drones can light the scene during static imaging with long exposure times. The potential of aerial autonomy also includes interaction with the environment, a functionality required in many documentation tasks. The potential for systematic applicability of autonomous drones in cultural preservation is almost limitless, and the objects of documentation interest range from artistic compositions to structural elements. To this day, the Dronument system has been used to document a plethora of such objects of interest for purposes of historical restoration and cultural preservation. These include paintings, where we observe small cracks, secondary sealing or dustiness of the surface, but also others such as frescoes, murals and structural damages, sculptures, stuccos, altars, walled actions of pulpitus, window frames, vaults, stained glass windows, mosaics, and many others. While capturing all these elements, the drone or teams of drones are deployed fully autonomously without human intervention. To learn more about the technology, please visit the papers and pages listed at the end of this video.